Everything we test or use to couple ultrasound attenuates ultrasonic pulses. Equation 1 indicates that the attenuation is a function of the distance x traveled in the sample thickness, and alpha, which is the attenuation coefficient, in dB per millimeter at 1 megahertz. And we see alpha is a function of frequency. As frequency increases, so too does the attenuation coefficient. We thought it would be interesting to assess the attenuation of several materials commonly used to make refracting wedges and delay lines. To this end, we set up a relatively simple experiment. We used an immersion through transmission technique to compare attenuation in 5 different materials using different thicknesses of each material. After capturing the waveform from each sample, the signal was converted to the frequency domain. Next, the spectral amplitude was converted to dB, normalizing the curves to the thinnest sample. Simply subtracting the dB difference from one curve to another at each frequency and dividing that by the thickness difference between the two samples being analyzed provides the attenuation coefficient in dB per millimeter for that frequency. Plotting each dB difference over a practical range of frequencies produces a curve showing the attenuation coefficient at each frequency. This allows us to apply a power trend line to the curve, which generates a reasonable approximation of the equation 2 seen on slide 2. A high R-squared value for the regression fit indicates how well the data trends as a power law. Materials used for wedges and delay lines are selected for different reasons: acoustic velocity, temperature resistance, impedance matching, attenuation, and even conformability, and all produce a downshift in the center frequency of the applied pulse. That downshift increases with thickness. Regardless which wedge material we use, we can see from the FFT plots that all these materials can allow some higher frequency content to pass. Slide 6 illustrates that even relatively high attenuation through thicker sections can be addressed with the proper selection of an initial pulse. So if the higher resolution of a high frequency content is required, the clue is to start with a well-damped, high bandwidth probe and adjust the pulsar to optimize bandwidth rather than trying to maximize energy output. When using a negative square wave pulsar, improved results will be had by shortening the pulse length and, if available, adding a bit of electronic damping to the pulsar.